This is the second video in anatomy of the gastrointestinal tract and also looking at digestion. What you can see down below is actually a picture of one of the very first studies that was ever done of digestion. This person is a fur trader, St. Martin, was shot in the abdomen, made a hole through the abdominal wall and through the stomach as well. They didn't think he would survive it very long, but surprisingly he did survive. And Beaumont studied digestion in him for about 10 years. The hole in the stomach actually healed to the hole in the abdominal wall so that there was this permanent fistula or entryway directly into the stomach. And so Beaumont could at different times take out some of the gastric juice and study it to see what was going on with digestion. All right, well, what is it that's digested in the stomach? And the answer is nothing completely. But we do begin protein digestion. Again, we've already talked about pepsin. It's a proteolytic enzyme, which means that it's a hydrolytic enzyme that attacks protein. And it is initially formed as pepsinogen, and again, that means that it's inactive. And it's the hydrochloric acid that actually alters the form of the protein a little bit to make it into the active enzyme. We also get a little bit further carbohydrate digestion, not a whole lot. As the food enters the stomach, it's still in the bolus. And so the inner part of that bolus is actually protected from the high acid. And so that won't inactivate the amylase just yet, but eventually the salivary amylase will be inactivated as that bolus gets mixed more and more and the acidity drops lower and lower. Remember that enzymes have pH optimums, and the optimum for the salivary amylase is far higher than the 2 that we find in the stomach. Well, what is it that's absorbed from the stomach? The answer is no nutrients, but some things are absorbed. Alcohol is absorbed here, and that's one of the reasons that you feel the effects of alcohol a little bit faster if you haven't had anything to eat for a number of hours. And then also some drugs such as aspirin. And again, drug manufacturers are always trying to find ways to get drugs into the system faster. And so they look at ways for drugs to be absorbed across the mucosa in the buccal cavity or the oral cavity and also in the stomach so that they can get in and start to work faster than they otherwise would. Gastric motility is really all about movement in the stomach. And so as we think about this, we can realize that there's still some mechanical digestion that is going on here in the stomach. And so the motility is first all about mixing. And so again, as that food came through into the stomach, it was at first a bolus, but it gradually becomes chyme as it mixed more and more with the gastric juices. And this also, as you can see here, does indeed reduce the size of the food particles. And so again, think about it. In this piece of food in the middle, the salivary amylase has not been inactivated by the pH of the stomach. But as it gets smaller, the amylase is more and more inactivated. Eventually, the food is going to get pushed down into the pylorus, and then from there it'll move through the pyloric sphincter and into the first part of the small intestine. And you can see that the food particles have gotten considerably smaller. Okay, and so initially this chyme is going to be acidic as it moves through there. This shows you another part of the mixing that occurs. And so interestingly, the outer parts of the chyme are a little bit more liquid. And as we move down into the narrow pylorus, you can see that it's the liquid parts that get pushed more towards the pyloric sphincter. And the more solid parts in the middle actually get pushed back to mix more completely. And so what's being represented by this yellow arrow is what's referred to as retropulsion, or the movement of the less liquid part back into the stomach to be mixed more and to break down those particles more completely. Well, gastric emptying, again, is just simply the movement of the chyme from the stomach into the intestine. And it's important that we understand this because it plays a role in such things as sports nutrition. There are factors in the stomach that affect how quickly the chyme will empty. And one of those is the amount of chyme. And in general, the more chyme, the faster it empties up to a point. At some point, the stomach is so distended that it slows down the mixing and it makes it harder for the stomach to break the particles of food down into smaller pieces. And so when you really fill up your stomach like you might at a big meal like Thanksgiving, it takes even longer to empty it than you might expect. The other thing that has an impact is size of the particles. If they're too big, that slows down emptying, and fluidity. If it's not fluid enough, that will slow down the emptying as well. And then there are factors in the beginning of the small intestine or the duodenum. And so there's a hormone produced here known as secretin that helps to inhibit production of hydrochloric acid. And the fat content of the stomach contents will actually slow down the emptying into the small intestine. And so if you've eaten a meal which is mostly fat, very high fat, it could take up to 6 hours for all of this to be emptied from your stomach. And then if the acidity is too high, if it's too hypertonic, or if we get too much distension, that also will slow down gastric emptying. And so all of these things are important when you think about something like a pregame meal before a basketball game, soccer game, football, whatever. Emptying of the stomach contents is also decreased by high exercise intensity. And so again, you may have heard, I don't know if you hear this as much as I did when I was a kid, but you don't go in swimming until 2 hours after you've eaten. Well, okay, maybe that's true. But really, high exercise intensity interferes with the stomach's ability to continue mechanical and chemical digestion. Hypohydration can also slow down gastric emptying, as can heat stress and strong emotions. All right, well, what is it that happens in the small intestine? Well, as a matter of fact, this is where the majority of digestion and absorption will occur. And we look at the anatomy of the small intestine. There are the 3 different parts. And so the first part, which is the shortest, is the duodenum or the duodenum. It doesn't really matter. You say potato, I say potato. And you can see that that's roughly a foot long, give or take a little bit. And then we have the jejunum, which is a little bit longer. And then finally, the longest part is the ileum, and it actually ends all the way down here at the ileocecal valve, because this part of the large intestine is the cecum, and so it takes a little bit longer for us to get down through and empty into there. Now, the truth is that the small intestine is actually shorter than we always used to think that it was, because we would look at the length of the small intestine in cadavers, and at that point, the longitudinal layer of the smooth muscle is completely relaxed. Well, when you're alive, it's never completely relaxed, and so that longitudinal layer would actually shorten the small intestine quite a bit. All right, now we're going to go ahead and look at the mucosa of the small intestine. Again, this is where most digestion and absorption occurs, and so this is very important. And as you look here, you can see these ridges, and these are known as circular folds that occur all along this tube. And one of the things that they do is they slow down the movement of the chyme along the small intestine, and that helps to make digestion absorption more complete. And so it allows it to occur to a greater extent. Here you can see that this is not the greatest picture in the world. It does show the blood supply here that gets in through the adventitia, but what is it that they've left out? Well, they've left out the lymphatic supply. And again, as we'll see later, the lymphatic supply is important for absorption of the fat in the diet. Well, here you can see that on the surface of these circular folds, we have what's referred to as a villus. And so the villus is this large bump, this finger-like projection that you can see right there. There it is. There's a villus. And there's another villus. And so these circular folds are covered with these villi. Okay, 1 is a villus, 2 would be villi. And you can also see here what they're showing you is that the surface of the villus is covered with these columnar epithelial cells with microvilli on the surface, and these are what are known as enterocytes. And so here you can see another depiction of one of the enterocytes. Here is a villus, and there's the enterocyte. And here are the microvilli on the surface of that. And here again, now you can see both the blood supply coming in and going up the length of the villus, but now you can also see that lymphatic capillary, which is known as a lacteal, which also comes in here. What is it that these folds, villi and microvilli, do for the small intestine? Well, you know that what they do is that they increase the surface area a tremendous amount. And they increase it more than 600 times over a tube of the same diameter that didn't have all this folding and this great expansion of surface area. And so that's part of the reason that we're so efficient at digesting and absorbing the stuff that we eat. Here we're just looking at a different depiction of the small intestine. And so again, here you can see the inner layer, the mucosa, with those circular folds. Underneath that, you can kind of make out the submucosa. And then here's the muscularis. And again, here's the longitudinal layer that is always at least partially contracted when you're alive, which again means that the small intestine is shorter than we at first thought that it was when we were pulling it out of a cadaver and looking at it. Here again is the serosa or the adventitia. And again, they should have not only arteriole in here, but they should have venual and lymphatic supply as well. And then here again, we can see greater detail of these circular folds. And so here you can see 3 of them. And you see that not all the circular folds are quite as large. And underneath it, again, you can see the submucosa. And now you can see, oh, look, there's a lymphatic supply, arteriole, venual. And don't forget that we also find a lot of lymphatic tissue in here, malt or galt, variously known as gut-associated or mucosa-associated lymphoid tissue. And then again, each one of these little finger-like projections that you see here is a villus. So lots and lots of villi covering these circular folds. And so here we can see one of those villi. And so here's a villus, and you can see that it extends all the way from here up to here. And now you can see those enterocytes that are covering the surface. And again, these are simple columnar epithelial cells, which have microvilli on the surface, and interspersed throughout here are goblet cells, which are responsible for making mucus. And again, mucus helps to lubricate and helps to move the stuff along a little bit better. And so here's our big nodule of gut-associated lymphoid tissue or mucosa-associated lymphoid tissue, because again, remember, this is the submucosa where we find this. Not shown well over here, but this is where we would find that galt or that malt in here. And then again, we see arteriolar and venual supply up deep into the villus. And also there's the lymphatic supply, and again, this is known as a lacteal, and it is going to be responsible for absorbing a lipid that's been digested in your diet. Interestingly, we could take out 50% of the small intestine and you would still digest and absorb almost all the nutrients in your diet. And so again, unfortunately, in today's day and age, we're very highly efficient at both digesting and absorbing nutrients. And so that means that we absorb almost all of the calories in our diet. Here you can see a photomicrograph of villi, and so you can see that the surface of those circular folds is covered with these things, and you get a better depiction of what's going on than from those two-dimensional pictures that we've looked at before. And so just lots and lots and lots of villi. You obviously can't see the enterocytes here in this particular picture, but now here you can see enterocytes with the microvilli on the surface of them. And in fact, what we're seeing here is one side of the small intestine and the other side, and here's the lumen. And this is where the chyme is moving through, and it's going to mix further with pancreatic juices so that it can be broken down more completely, and then we'll start the process of absorption as well. And the final part of digestion actually takes place in the phospholipid bilayer of the microvilli, and that's where the absorption will also take place, and we'll look at that in video number 3. Here again you can see the microvilli on one side. Again, here's the lumen, and this is where the chyme and the pancreatic juice will mix together. And this shows you what happens when somebody has a gluten enteropathy. And the truth is that very few people have gluten enteropathy. Estimates are that it's about 1 to 3%. There are several researchers, 3 primary researchers, who think that that might actually be as high as 6%. But you've got to remember that that means that as much as 94% of the population has no gluten enteropathy, and there's no problem with getting gluten for you. And in fact, whole wheat is good for you, and it's healthy for you, and it's far healthier for you than sugar. We'd see a lot less chronic disease if we cut sugar out of our diet than we see by cutting gluten out of our diet. And so you go to the restaurant and you see all these gluten-free options. Most of you can ignore those, and you should cut way back on the sugar and the fat in your diet. Okay, what is the role of the pancreas in digestion? And the pancreas, as we've mentioned before, we talked about the pancreas when we did the endocrine system, but it's a mixture of both exocrine and endocrine tissue. And the exocrine secretions that it makes a lot of water, and so it's adding water here into the small intestine. But then again, hydrolytic enzymes, also sodium bicarbonate, and that sodium bicarbonate will dissociate to sodium and bicarbonate, and the bicarbonate will buffer lots of the protons that have come through from the stomach as the acidic chyme gets moved in here, and so now it's going to convert that into a basic mixture as it mixes there. The enzymes that are produced, we have proteolytic enzymes. And so again, proteolytic enzymes are hydrolytic enzymes that attack protein. And again, look, trypsinogen, chymotrypsinogen, and pro-carboxypeptidase. And so when these things are first produced, they're inactive, and they have to be activated by cutting off the part so that we end up with trypsin, chymotrypsin, and carboxypeptidase. And those are the proteolytic enzymes that are working here in the small intestine. Pancreatic amylase, you might remember salivary amylase began the process of carbohydrate digestion, and now pancreatic amylase is going to continue it, and again it'll be finished up in the brush border and the microvilli. And then also the pancreas is producing lipase, which does the majority of the hydrolytic digestion of the lipid. Which enzymes absorb nutrients? And that's a trick question. The answer is enzymes don't absorb the nutrients. They break them down, they hydrolyze them. And so again, this is a common mistake that's been made in the past, and so I'm trying to point out to you that enzymes don't absorb. Enzymes are hydrolytic, and they break these macronutrients down into smaller and smaller particles. Again, remember, which nutrients don't need to be digested? And you should have said, well, water doesn't have to be digested. Vitamins and minerals don't have to be digested. So what we're digesting would be protein and carbohydrate and lipid. Okay. And so here again, now we can see the pancreas, but we also see the gallbladder. And so the pancreas is involved in processing nutrients as well. And we've already talked quite a bit about insulin and how insulin is the one and only energy storage hormone. And so it's storing not only the carbohydrate, the glucose, but also amino acids and fatty acids. And then the major antagonistic hormone is glucagon. And so when blood glucose levels are lower, glucagon is increased to try and help keep blood glucose from dropping further and stimulating the production of glucose. And then another one that we find is somatostatin, which we're not really going to talk about, and it helps to suppress the release of hormones of the gastrointestinal system. And then here we can see some of the ductwork of the gallbladder and the pancreas. And so here again is the gallbladder. The gallbladder is really just an organ that stores bile. And there's the bile, this deep green. It's even darker green than that. And here you can see what's referred to as the cystic duct. That's how the bile is going to get into the small intestine. Here's the common hepatic duct, and so it's coming from the liver. And those two things merge to form the common bile duct. And so here it is, the common bile duct coming down that way. Here is the main pancreatic duct. And you can see that those two, the common bile duct and the main pancreatic duct, meet here at the hepatopancreatic ampulla. Ampulla was a vessel in Latin. In ancient Rome, it was a two-handled vessel that would hold a variety of things. And then here we can see the major duodenal papilla. And you might remember from the study of the kidney that a papilla is a nipple. And so this is how those juices, the bile and other things coming from the liver and the pancreatic digestive juices will actually enter early on in the small intestine and begin to mix with the chyme. Okay. And then here you can see another depiction of that. And so now you can see an enlargement and a cross section. Here is the common bile duct coming in here. Here's the pancreatic duct. And then again, this is that hepatopancreatic ampulla where those juices will mix together. This is a sphincter. And then here is that major duodenal papilla. And this is again where those juices are going to go ahead and enter the small intestine. Where is the bile produced? Well, the bile, again, is only stored here in the gallbladder. It's not produced here. The bile is produced in the liver. Here we're looking at up from the underside of the liver, and here's the gallbladder. And so when we're looking straight on at a person, usually we can only see the very tip or none of the gallbladder at all. The liver actually has 4 lobes. I'm not sure how important those are because surgeons don't care about the 4 lobes. Recent research has suggested that from a functional standpoint, we should divide the liver into 9 segments. And so we're not going to do that right now, but down the road, we're more than likely going to see the liver being talked about slightly differently. And 9 segments rather than 4 lobes. And again, here you can see that cystic duct. And over here you can see the hepatic duct. And so they will merge to form the common bile duct, which later on dumps into that ampulla. What about the blood supply to the liver? And so you look here and you can see here's the hepatic artery, which is actually coming from the abdominal aorta. And so the hepatic artery is coming in here. And this is the hepatic portal vein, which we'll talk about more in a minute. Well, what differences exist between the hepatic artery and the hepatic portal vein? You can see that the hepatic artery is bringing in blood directly from the abdominal aorta, and it's nice and highly oxygenated. The blood in the hepatic portal vein has had some, but not all, of the oxygen removed. Here again, we're looking at a frontal view of the liver, and you can see that the inferior vena cava actually runs up from here and goes up behind the liver, comes out on the top. And then again, here you can see the bottom of the gallbladder peeking out from underneath. And now what we're doing is we're looking from behind, and so this is the back view, and now you can see the inferior vena cava running up, and you can even see that the liver is actually kind of wrapping around the vena cava to an extent. And here we get a better depiction of the blood coming from the GI organs. And so here is the inferior mesenteric artery, and you can see it primarily comes from a part of the small intestine, and this is descending colon, sigmoid colon, and the rectum. And then here is the superior mesenteric artery, and here we get the ascending and transverse colon, and also most of the small intestine. And then here you can see the splenic artery, and these things merge and form the hepatic portal vein moving up into here. And so again, you might remember what is it that makes something into a portal system, and we talked about this when we talked about the hypothalamus and the anterior pituitary. And so we're coming from the capillaries of the digestive organs, small intestine, large intestine. We're going through a vein and we're going to a second capillary bed. And so we're going to the capillaries of the liver. And that is what makes this into a portal vein. And here you can see a schematic of that. And so here are the capillaries that are in the stomach and the intestines. Here are the capillaries in the liver, and here's the portal vein which links those two sets of capillaries. Okay. And then again, here you can see a little bit more clearly the blood supply to the liver. Here's the hepatic artery, and here is that portal vein. Interestingly, the portal vein is actually supplying 40% of the oxygen to the liver. And so remember that when blood goes through a capillary, not all the oxygen is taken out. Typically, the PVO2 will still be at 40 millimeters of mercury. So there's still a significant amount of oxygen in this blood. Now, that means that the hepatic artery is supplying about 60% of the O2 over here to the liver. So about 60%, and again, I'm doing this writing, which I know isn't real good. And I've got to cut that out, don't I? 60% of the O2, and again, hepatic portal vein is supplying about 40% of that O2. All right, well, now we're going to look at the organization of the liver on the inside, and it is organized into what are called these hepatic lobules. And here you can see 3 and part of a 4th lobule as you look at this. This picture is trying to help you understand what a lobule looks like, and so we've taken this book and we've folded the cover back on itself. The pages didn't open up quite as nicely as I would have liked, but the pages represent a sheet of hepatocytes. That's what they represent. And then down the middle of the book cover, we have that central venule that goes down through there. And so that's the central vein that eventually is going to make its way back to the inferior vena cava. And so that's what you've got there. How big are these lobules? Well, they're pretty tiny. They're smaller than these sesame seeds that you see here in the hand. And so they're fairly small. What are the cells of the hepatic lobule? Well, they're mostly hepatocytes. That's what they are. You can't see them real well here, but in the next slide we'll get a better depiction of those hepatocytes. And again, 80% of the cells that we find here are hepatocytes. And then finally we get to some sinusoidal capillaries. Pause the video and remind yourself what is true of the sinusoidal capillaries. And you should have said that these are the leakiest of all. They have big holes in them. Because we've got to have exchange of tremendous amounts of material. And so that's what's going on as we look at this. And so we're delivering nutrients, chemicals, toxins to the hepatic lobules to be processed so that we can do that. And here we have a slightly more schematic depiction of what's happening out here at the very edge of this. You can see that we've got a portal venule, and we've got a branch of the hepatic artery, and then we've got a bile duct, which all come together here. And then here the blood is moving through. and it makes its way to that central vein again, which is over here. And then you can see that this is lined with hepatocytes or liver cells, but you can also see other cells. This is actually a macrophage. It used to be known as a Kupffer cell. It's a macrophage which is restricted to these liver lobules. And here you can see a better depiction of this, and now you can make out those individual hepatocytes, and you can see that we have these very regular arrays, and they go down as well as out this way. So you got to remember it's kind of three-dimensional, and they run down that way. And so think of that page before. Again, here are those hepatic sinusoids, which have big holes in them. And then here we have the three parts here: hepatic artery, hepatic portal venule, and then the bile ductule. And you can see the flow of the bile is in the opposite direction. And then there's that central vein. If we don't count the skin, the liver is the largest organ, and it does indeed process the macronutrients, protein, carbohydrate, fat. It also detoxifies wastes like alcohol, hormones, drugs, and those drugs could be recreational drugs or they could be medication that you take. It does store stuff, including glycogen, fat, iron, copper, vitamins. It is responsible for activating vitamin D. It does help to remove bacteria and worn out red blood cells. And again, we have those hepatic macrophages that I showed you. And here you can see them in this picture right down here. There are those hepatic macrophages. And then we also get rid of the bile. And so bile is a combination of bile salts, bilirubin, and cholesterol that are involved in the digestion of only fats and not carbohydrate or protein. And here's another depiction of all of that. And again, here you can see those stacks, columns, and rows of hepatocytes that surround these sinusoidal capillaries. And here again are the macrophages, two different pictures of those. And we also have dendritic cells in here, which are APCs. Now, the other thing that I wanted to mention to you is that we've got different liver diseases, and one of the more worrying right now is what's known as non-alcoholic fatty liver disease, which I believe I've already mentioned to you. The primary cause of non-alcoholic fatty liver disease is overconsumption of sugar, and that could be sugar that's added to food and you don't see, or sugar that you're adding yourself. And there is so much added sugar in foods that people in today's day and age are just getting way too much sugar, and we'll talk about that more later on. But we're starting to see 20% of people with non-alcoholic fatty liver disease, NAFLD, that has actually progressed into non-alcoholic steatohepatitis, which is more serious, and so not a good thing. NAFLD is the most common form of chronic liver disease, most common. 1 in 5 adults have it and 1 in 10 children. Okay, 60% of obese adults and 50% of obese children have this. And this is really, really concerning that kids would have NAFLD. And NAFLD and NASH are linked to obesity. And we've got epidemic levels of obesity, high blood sugar, insulin resistance, high plasma lipids, and especially triglycerides. And triglycerides are not only linked to high fat consumption, but also high sugar consumption. And so high sugar also leads to high triglycerides. And that brings us to the end of video number 2. And in video number 3, we're going to focus more on the digestion and absorption of the macronutrients.